let's talk about the proper time and proper velocity in relativistic mechanics, right? So before I do that, I'm just going to briefly go over some of the rules of relativity, and they go like this, right? So rule number 1 is that no point of view has preference over any other point of view. What that means is that all the point of views or all inertial frame of references are equivalent, right? So, and moving on to rule number 2, it says that every observer carries their own set of coordinates and their own clock, right? Okay, so rule number 3 is then that if one of the observer wants to make a measurement for a different observer, then they need a coordinate transformation. Moving on to rule number 4, it states that it will always appear to an observer that they are stationary in space, right? And so all the other things are actually moving. Okay, so lastly, moving on to rule number 5, the space-time path is invariant under a coordinate transformation. So what that means is that if you go from one person's coordinate system to another person's coordinate system, the space-time path is going to remain unchanged. So what is this? The space-time path is actually the distance between the 2 points or 2 events or 2 successive events, right? Okay, so with that out of the way now, let's go ahead and talk about the proper time. Proper time, right? Okay, so now relative to a fixed inertial frame is just actually a non-accelerating frame, right? So now in this, as you move along the world line, which is a space-time path, your watch actually runs slower and slower, right? Now the question is then how slow? And well, that is then the dilation factor, and whether it's large or small, that depends on the speed, right? On your speed. Now, if you recall that you can write, or the invariant interval is actually defined as ds squared is equal to c squared dt squared minus dx vector, right, squared. Okay, and well, this is the space-time separation, and it can come from the fact that in 3D space, the space-time between 2 points, say x1, y1, z1, and some x0, y0, z0, that can be written as your delta L squared is equal to delta x squared plus delta y squared plus delta z squared, right? And so for your, if you Carter for time, right, which is actually your c dt, that is your x0, if you Carter for that, then you can write your space-time interval as this equation over here, right? Okay, so also note that again that the distance between these 2 points in space-time remains invariant under the transformation, which is again one of the rules that we said, that the space-time path between the coordinate transformation actually remains unvariant, right, or invariant. Okay, so now let's talk about a frame that's a rest frame. So in a rest frame, say S of the observer, your dx will actually be 0, right? Because it's a rest frame, so it's not moving, and therefore the difference in the position is going to be null, right? So that means it's not moving. And so with that the case, then we can write, let's call first this equation 1. So equation 1 can be written as then simply ds squared is equal to c squared dt squared, right? Okay, so now let's go to the next slide. And in frame S prime, now this S prime is a frame that is moving with respect to the frame S, and so we are calling it just S prime. And so in that S prime, the invariant interval can be written as ds prime squared is equal to c squared dt squared minus dx vector, right, prime squared, right? Now remember that your metric tensor, that is g mu nu, is or can be written as, in this shorthand notation, 1 0 0 minus 1 tilde. So minus 1 tilde is then distributed over all your space or spatial components, right? And so this is just one of the conventions that says that I'm writing my metric tensor as 1 minus 1 minus 1 minus 1, right? And so you could also write it as minus 1 plus 1 plus 1 plus 1. So that's totally up to you, but you have to stick with one of the convention and then carry out all of the calculations, right? Okay, so with this then I can rewrite my space-time interval as ds prime squared is equal to g mu nu times dx prime mu times dx prime nu. So now this is how you can write this equation over here as well, right? And so if you note that you can reopen this thing in terms of this equation, or it will become this equation over here, right? Because your g mu nu, so g 0 0 for your time part is positive 1, and x 0, this thing over here, x 0 is your c dt. And so taking this dot product or contracting the two vectors, your x0 would then be x0 squared. You could write it as, let me actually do it neatly. Yeah, you could say that it's this thing over here, so c squared dt squared, roughly speaking, right? Okay, so well, with this then we can define now the proper time, which is an invariant quantity, right? And so the proper time can be defined as d tau squared is equal to ds squared over c squared, right? Okay, so this then obviously quickly implies that your d tau is equal to ds over c, and this comes then from the equation for your rest frame, right, which was this one, right? So from here we were able to define the proper time as this thing over here. And now let's move on to the next slide and write this thing, that ds is actually equal to, or ds squared is actually equal to ds prime squared, And then this is again from the fact that the distance between the 2 points in space-time are actually going to remain invariant under a transformation. And so then this thing over here is that distance, and so it's going to remain invariant if you change the coordinate systems, right? Okay, so then with this, then we can write our d tau being equal to ds prime over c, right? Which is then 1 over c times, let's first go back over here. So if you remember, this is how we wrote our ds prime squared. So ds prime would be then the square root of this quantity. So let me just write it down here. So it would be this square root g mu nu times dx prime mu times dx prime nu, right? But also, since g mu nu times dx mu times dx nu is equal to g mu nu dx prime mu times dx prime nu, right? This is I've just written ds prime squared, right? Which, let me go back again. This was this thing over here, right? And so I said over here that the space-time path is invariant, and so then this over here is then obviously true, right? So then with this I can write my d tau equal to 1 over c times the square root of g 0 0 times dx contravariant 0 squared plus g 1 1 dx 1 squared plus g 2 2 dx 2 squared plus g 3 3 dx dx 3 squared, right? Okay, so all I have done is substituted this in this equation over here, right, in the square root. So with my mu and nu both going from, mu and nu are actually 0, 1, 2 and 3. 0 obviously for the time component, and 1, 2 and 3 are for the spatial components. Okay, so now if you look at this equation over here, you know that your g00 is -1 and your dx0, this thing, is c dt, right? And so then this thing over, this quantity over here would give you -c squared dt squared, right? And we know g11 is +1 and dx1 can be written as just simply your basis vector x, and so this thing would give you dx squared. And likewise g22 is +1 again, and dx2 or x2 can be thought of as your basis vector y, and so this would be dy squared, and likewise for this quantity over here. So let's go ahead and then write this down. D tau squared is equal to 1 over c times the square root of your c squared dt squared. Now if I go back over here, right, from this g11, g22, I'm sorry, I might have said before that my g11, g22 and g33 are +1, but they're actually -1, remember, because that's how, if you go back over here, that is how we defined our metric, right? Okay, so let's come back here, and now your you would have a negative sign with this quantity over here. You would also have a negative sign with this quantity over here because of your G11, G22, and you would also have a negative sign with this quantity over here, that is because of G33. And so we could take or factor that negative sign outside, and so we would have negative dx squared plus dy squared plus dz squared, right? And this is your square root. Close the bracket. Right. Now, if you recall that the velocity squared of an object can be written as x dot squared plus y dot squared plus z dot squared, right? And x dot is, let me actually write it over here, x dot is actually my dx over dt. So it's the time derivative of position coordinate. Sometimes I write it as d subscript t of x, right? Okay, so that's what that is. So now let me get rid of this. Okay, so this now is the velocity of the object, right? And so we can now substitute for this in this above equation over here and write our d tau as 1 over c, but we could also factor or take this c squared dt squared outside, and once we do that we would have c squared dt squared square root of that, and that would be then simply c dt, right? And we would be left with inside the square root as 1 minus, now if you look at this, you have dt, you have factored a dt outside, right? So with this quantity over here, there will be a dt in the denominator, right? And so that would be dx squared over dt squared, right? So what is that? That is simply your x squared, and likewise for dy squared and dz squared. So that whole thing would give you actually v squared, right? Over, because we have factored a c squared outside as well, so we would have a c squared over here. Now, if you recall what this quantity in the square root actually is, it's the Lorentz factor 1 over square root 1 minus v squared over c squared is your gamma, right? And so then you can write your proper time in terms of gamma. Actually, let me go back here. We can also see that your c and c cancels out, and your or I'll just write it over here, right? So it turns out to be that your d tau proper time is gamma, this thing, right? It will be actually 1 over gamma, right? So 1 over gamma times dt, right? So let's just go ahead on the next slide and write it down, that your d tau is 1 over gamma times dt, right? So let's just box this over here, and this over here, tau is the time that your watch registers, and it is called the proper time, right? It's the time that is actually associated with the moving object. Now, because tau, the proper time, is invariant, that is, it does not cares about the frame of reference, right? So it is then more relevant than the ordinary time t, right? So we end up using the proper time in most of our cases or problems, right? Okay, so now that we have defined the proper time, we can move on to something that's called the proper velocity, right? The proper velocity of the object. Now let's start this with an example. suppose that a passenger is on a flight and the captain announces that the speed of the aircraft is, say, approximately 4/5 times the speed of light, right? So what does he precisely means by the term speed? Well, obviously the answer comes to the mind that yes, he means that the distance traveled per unit time, right? And so that distance traveled per unit time is actually your u. So u vector is equal to the time derivative of your length, or the distance traveled, right? So L vector. Now, since he is talking about the speed relative to the ground, both L and T will be measured by an observer who is on the ground, right? So let's go ahead and define a quantity, a hybrid quantity called the proper velocity. So I'm going to define it as eta as my proper velocity is equal to d tau, the time derivative with respect to the proper time, right, of my L, right, the vector L, which is then equal to, because if you see from this equation, I can write it in terms of gamma, so that is gamma times the time derivative, the ordinary time here, of my distance L, right? And so I can move on and write my proper velocity as eta vector is equal to 1 over under root 1 minus v squared over c squared, right? And of course times your vector u, right? So this over here is then your proper velocity, and this is obviously for speeds that are v that are much smaller than the speed of light, right? So in I mean, this over here is actually it is for speeds that are going to approach speed of light, right? And for this is something else now. For speeds that are smaller than the speed of light, then your eta is actually equal to your u, right? So you don't need to multiply that gamma factor over there, right? Okay, so now we can also, we are practically done with this, but we can write this in terms of the 4-vector formalism. And so it is pretty direct then to see that you can write your eta mu equals to d tau, the time derivative with respect the proper time derivative of your x mu, right? Now from this then you know that your eta 0 would then be your proper time derivative of x 0, and what would that be? That would then be your c d proper time derivative of your ordinary time t. But if you recall from here, right, this thing, that you can write your d tau as 1 over gamma times dt, and so what do you have over here is actually the inverse of that, d tau of your ordinary time t. So you could write your eta 0 as, or this is the proper velocity time component, as c times gamma, right? Because the proper time derivative of your ordinary time from, again, this quantity over here is your gamma, right? Okay, so I can then expand this obviously as c over the under root of 1 minus v squared over c squared. Now we can use this result, right, and then write it generally for all eta i's, right? So let's go on to the next page, and we can then obviously write in general that your eta I, the proper velocity components, is going to be v I over under the root 1 minus v squared over c squared, right? So I wrote this again from looking at this over here, right? Okay, so now we have defined our proper velocity in terms of the 4-vector formalism as well. So that now we're at it, let's actually see how this proper velocity transforms under the Lorentz transformation. So your Lorentz transformation matrix is given by, and note that this Lorentz transformation matrix, it's a mixed tensor actually, and the one that I'm going to write it for is if your particle or an object is moving along the x-axis, right? So this is not the general transformation matrix, it is for a particular case. So it's gamma minus gamma times beta, but beta is actually my v over c, right? So beta 0 0, and I have negative gamma beta gamma, again 0 0, then I have 0 0 0 0 1 0 0 1, right? Okay, so this is your I don't know, I might have called this gamma, but it's actually lambda, and it's a mixed tensor, and it's your Lorentz transformation matrix for a particular case when your particle is moving along x-axis. So then with this, then it is pretty straightforward to write the proper velocity under a Lorentz transformation, right? Because all we have to do is transform this velocity over here with the action of this transformation matrix, right? So what that means is, all I'm going to do is then write my eta prime, which is the proper velocity component mu, is equal to my lambda mu nu x nu, right? And so let's expand this, right? And if I do that, I can write my eta mu as lambda mu 0. Now note that we have sum over the repeated indexes, right? That is using the Einstein's summation notation. So I'll have x 0 plus lambda mu 1 x1 plus lambda mu 2 x2 plus lambda mu 3 x3. So again, mu is for 0, 1, 2 and 3. So if I substitute for mu as well, I can then write all the components of eta as, let me write it down, eta 0, eta prime 0 is then going to be my lambda 0 0 x 0 plus lambda 1 1 x1, sorry, it would be lambda 0 1 x1 plus lambda 0 2 x2 plus lambda 0 3 x3, right? I have 0 in superscripts or the upper index because I'm doing it for eta prime 0, which is the time component of your proper velocity, right? And then likewise you can do for eta prime 1 as lambda 1 0 x0 plus lambda 1 1 x1 plus lambda 1 2 x2 plus lambda 1 3 x3. And then let me just do for eta prime 2 lambda 2 0 x0 plus lambda 2 1 x1 plus lambda 2 2 x2 plus lambda 2 3 x3, right? And then likewise for eta prime 3 as well. Or let me just write it down. It's just one more expression, right? So lambda 3 0 x0 plus lambda 3 1 x1 plus lambda 3 2 x2 plus lambda 3 3 x3. So I have written all of them using this thing over here, and then this thing was expanded to this thing over here, and then using this, then I have written all my proper velocity components under obviously the Lorentz transform. So that prime on eta stands for that this is how your proper velocity components are going to transform, right? So we can then write this in the matrix form. So let me write that down. So in matrix form, I can write it as I'll first write down the components, then I'll put the brackets, right? So eta prime 0, eta prime, I'll leave more space, eta prime 1, eta prime 2, and then finally eta prime 3, right? And now let's put this in a column vector or the matrix form, and then the transformation matrix is then going to be your Lorentz transformation matrix, and the components can be in general written as, okay, let me write them down, lambda 0 0, lambda 0 1, lambda 0 2, lambda 0 3, and now lambda 1 0, lambda 1 1, lambda 1 2, lambda 1 3, right? And likewise lambda 2 0, lambda 2 1, lambda 2 2, lambda 2 3, lambda 2 now we'd be having lambda 3, so lambda 3 0, lambda 3 1, lambda 3 2, lambda 3 3, right? And now let's close this bracket as well. Okay, so now if you look at it, your mixed tensor, when writing in terms of a row and column matrix, the upper index actually specifies your row. So this is your 0th row, or you could also say that this is your first row, but the 0th is for actually the time component, right? And then you have your second row, which or let me just say that this first is actually your 0th row, then you have your first row, and so for that you have 1 in the upper index, and the lower index is then for your columns, right? Okay, so let me get rid of these lines that I just drew. Okay, and then obviously this matrix is going to act on my eta 0, right, without the prime now, because these are going to be your original or the untransformed proper velocities, right? Eta 1, eta 2, and finally eta 3, right? And so this is then how you would see how the proper velocity transforms under the Lorentz transformation. And it would actually be a very good exercise now for you to write these components of the transformation matrix and then write down the expressions for your transformed proper velocities, right? Opening these components of the transformation matrix. Right, so then this was it on the proper time and proper velocity in relativistic mechanics, and I hope that this video helped you in a way and you understood the idea and the concept of the proper time and proper velocity and how to mathematically write it down, right? Okay, so that's it.